Hi friends, welcome to LGF. So today we have to start the 10th lecture. In the lecture 9, we discuss about the second order system transfer function, correct? So the transfer function of the second order, we have seen omega n square divided by s square plus 2 del omega ns plus omega n square. This one is the very important, you have to remember, okay? Where omega n is the natural frequency of oscillation, zeta is the damping ratio, okay? So if zeta omega n is given, this is your damping factor. This is the damping factor. Omega n is the natural frequency of oscillation, zeta is the damping ratio, okay? And the multiplication of both these parameters is nothing but the damping factor. Okay, last time we discussed about that second order system response is depends on zeta value only, correct? What it means that if you have second order system, you are going to apply some input to it, you are getting some output from it, correct? So the nature of this output will be decided by this zeta, correct? So this is the third party which is affecting the relation between input and output, okay? So this is outsider, correct? So now let's start. We'll apply different inputs to the system. This is the second order system. We'll apply unit impulse, unit step, ramp and parabola. We'll see the output, correct? So we'll see the impulse response of the second order system. Friends, the transfer function for the second order is Cs by Rs. Again I'm writing over here omega n square s square plus 2 del omega ns plus omega n square, okay? Your input is RT, input is del T, okay? Your Rs is 1, okay? So put Rs equal to 1 over here, you will get Cs is nothing but omega n square s square plus 2 del omega n plus omega n square. Can you draw now the output waveform? No, you cannot, because this zeta parameter is given over here in the equation. Your output is depend on zeta values, correct? Omega n and all. So omega n is the frequency, no problem at all, but this zeta is the damping ratio which is going to decide what will be the output. Let's take the various conditions of this zeta when zeta is equal to 0. If zeta is equal to 0, and this is the characteristic equation, this is the characteristic equation of your system, second order system, and this characteristic equation is going to decide the number of poles, whether they are in the RHS or they are in the LHS. So we can easily identify whether the system is stable or unstable or the marginally stable, okay? So if zeta is 0, your system characteristic equation is s square plus omega n square equal to 0. So it means you have omega n. This is the condition. You have poles at imaginary axis. What it means, at zeta equal to 0, we have seen earlier, if your poles lie on the imaginary axis, the system is marginally stable. Marginally stable. Marginally stable means it's going to be oscillate. It will provide the sustained oscillations, correct friends? So if zeta is 0, your output will be oscillating. See, this is the oscillation and the frequency of oscillation is this. So input is zeta, output will be sustained oscillation. Sustained oscillation, you can see over here, it's like this. it's like this. If zeta is 0, you are getting sustained oscillation or natural oscillation, I call it. Okay, so at omega equal to 0, I call it undamped. Okay, this is undamped system. So the output of the undamped system will be sustained oscillation. Okay friends, now if you'll apply this system, we have seen at zeta equal to 0, the nature of the output is sustained oscillation. This is the second order system whose zeta is equal to 0. Now we are providing different inputs to it. If you will provide the unit step, your output will be like this. This is the unit step. Across this you will get oscillation like this. You will get oscillations. If this is unit ramp, so unit ramp is like this. So your oscillation will be like this. Across this, your system will oscillate continuously. Why system is oscillating? Because your zeta is 0. This zeta is 0, it means undamped system. Undamped system means it will oscillate continuously. Correct. Now instead of this, if your input is parabola, so for the parabola, the output response will like this. Sustained oscillation. Okay, so the point now it's clearly, see the point we have seen, the nature of the output is depends on zeta values, on the zeta values. Whatever the zeta value is there, based on that we'll say what is the output nature. Correct. In this case zeta equal to 0, so output is sustained oscillation. Now the next condition, in the next condition we'll see zeta equal to exactly 1. But before come to 1, let's come 0 to 1. Okay, so here this is your zeta range. In this case again I'm considering the characteristic equation, and that is a square plus 2 del omega ns plus 1. Correct. Here your zeta range is given. Zeta is from 0 to 1. In this case you will get s values, number of poles you will get. Okay, let's take s1 and s2. Definitely you will get 2 only, because order of the equation is 2. So when you will solve the equation, which equation? This equation, you will get number of poles are minus zeta omega n plus minus zeta omega n 1 minus zeta square. Okay, so you are getting complex root for this range. It's kind of like this. Okay, this is the S plane I'm considering over here, minus zeta omega n. Here this is the point of minus zeta omega n. So you are getting one pole at this place and one at this. So this is given minus j omega n 1 minus zeta square. Over here this will be j omega n 1 minus zeta square. Okay, so this is the for zeta range 0 to 1, your system response. Correct. Now let's come over here. Let me change the pen first. Friends, earlier we discussed about the time constant. Time constant is given by minus 1 upon this real part. So it's given minus zeta omega n, reciprocal of this. Okay, so real part of the the system. Correct. So it will become 1 by zeta omega n. Okay, so this is the time constant given by like this. Okay, minus 1 divided by real part of the system poles, correct? Now this term is nothing but omega d, damped frequency, that is omega n 1 minus zeta square. Correct? Your system is damped in this case. Why? Because you have considered your zeta damping ratio value in between 0 to 1. Your system will not oscillate continuously now. It will be damped oscillation. Definitely it will oscillate, but the oscillation will die out. Correct? So come over here. Your system is second order system. The zeta value you have, take in this way. See, zeta in between 0 to 1. Now we have seen, according to the characteristic equation, that output will be damped oscillation. When zeta is in between 0 to 1, the poles are in the left of S plane, which are complex conjugate. Yes, we calculated this one, right? Remember the poles we have calculated, minus zeta omega n plus minus j omega n 1 minus zeta square. These are the complex conjugate if your limit of the 0 or the range of the 0 is 0 to 1. Okay. Then system response will be exponentially decay oscillation, called the damped oscillation, and system called the underdamped system. So it will be like your system output will be like this, decaying oscillation, like this. At t equal to infinity, your oscillation will die out. Correct? So for the different inputs, you'll get the different outputs. Okay, but nature of the output will same, because nature is going to decide by the zeta only. If you remember, when zeta was 0, this was undamped system, and output nature was sustained oscillation. When zeta in between 0 to 1, you are getting underdamped system. Underdamped system means, now if in this case you are getting sustained oscillation, now the system is damped because you applied some zeta, and zeta is the damping ratio. You'll get the output oscillation or the decayed oscillation. Correct? Now we'll see zeta is equal to 0, suppose. Now we'll see for the zeta equal to 0. Oh sorry, zeta equal to 1. Okay. What is the characteristic equation? If you remember, a square plus 2 del omega ns plus omega n square, correct, equal to 0. Now your zeta is exactly 1, so it will be a square plus 2 omega ns plus omega n square. So this is nothing but s omega n whole square equal to 0. So s is nothing but minus omega n minus omega n. So it's kind of like this. See, two poles are repeated at the same point, and that is omega n. What will be the time response of the system? The time response of the system will be 1 by omega n, and it will be minus. So minus minus will become plus. Correct? And if I'll ask you, what is the omega d? What is the imaginary part over here? It's a 0. So there is a no frequency, no oscillations will be there over here. Is it okay? So this condition is called the critical damped system. When zeta equal to 1, your system will be critical damped system. Okay, so in this condition you will not get any oscillation in the system output. Correct? Now we'll consider the values for zeta is greater than 1. Over here, this will be overdamped system. Overdamped system. Okay. So in this case, you will get S is nothing but minus zeta omega n plus minus omega n zeta square minus 1. This is not the complex one. Okay. In this condition, you'll get one pole near to imaginary axis and one pole away from the imaginary axis. Correct. Over here also, what is the time constant? The time constant tau is minus 1 upon real part of the pole C. This is minus zeta omega n. This will cancel out, and no, this is the entire part you will consider over here. Okay, so dominant pole we will consider over here, and that is which one? Zeta omega n minus, this is already minus, correct? So minus minus will become plus. Finally you'll get zeta omega n, and over here omega n zeta square minus 1. This will be your time constant. Okay, for if you are having two poles like this, you have to consider the dominant pole. This one is the dominant pole. Okay, the pole which is near to the imaginary axis will give the time constant. Correct. So this is the case for overdamped system. So now we can conclude it. Correct. The conclusion will be, if your zeta is 0, it is undamped system. If your zeta is in between 0 to 1, this is underdamped system. If your zeta is exactly 1, this is critical damped system. Correct. If your zeta is greater than 1, this is overdamped system. Okay, so let's come to the summary now. Correct. So at exactly zeta equal to 0, we got two values of the poles, plus minus j omega n. So this is plus j omega n, this is minus j omega n on the imaginary axis. Is it correct? So here the system nature is oscillatory. Correct. For the zeta equal to 0, we have seen the natural oscillation. Correct. And the system is undamped system. Then we have seen zeta in between 0 to 1. For 0 to 1, we got the complex conjugate poles. So these are the poles for what? For zeta in between 0 to 1. In this case, we have seen the damped oscillation. The output was like this, damped oscillation. Means at t equal to infinity, it will die out. The oscillation will die out. Correct. Then we got this value at zeta equal to 1 exactly. If you remember, at zeta equal to 1, we got two values, omega n minus omega n minus omega n. And if you remember this is the complex poles given over here, and the real part was zeta omega n, if you remember, and the frequency part we got, it is j omega n 1 minus zeta square. Okay, in this case the poles were like minus zeta omega n plus j plus minus j omega n 1 minus zeta square, if you remember, like this. Okay, now in this case we got two poles, repeated poles at the same point. Now for the overdamped system, if you remember, we got S is minus zeta omega n plus minus omega n zeta square minus 1. So one pole is at this location and one pole is at this location. Correct. So this location pole is minus zeta omega n plus omega n zeta square minus 1, and the pole which is away from the imaginary axis is minus zeta omega n minus omega n zeta square minus 1. Okay, So this entire summary is based on the system behavior for different values of zeta. Correct. Now friends, over here the system is underdamped. Over here the system is critically damped. Critical damped system. And for this and this, the system is overdamped system. This is overdamped system. Okay, so this is all about this lecture. We'll continue with the same thing in the next. Correct? So in the next lecture we'll discuss the time domain analysis for the second order and the first order systems. Okay, so friends, for the new updates you can subscribe the LGF. For doubt solving you can find us on the Facebook. We'll meet in the next. Till then, take care and bye.